Pulleys and wedges, type 1, one string, common tension, and this is A horizontal. So in 2005 we were giving a particle of mass 4 kilograms resting on a rough surface. So rough horizontal surface is important because that means that friction is going to come into play. It's connected by a light inextensible string. So inextensible string means that it's not going to be elasticated. So we're not going to have bouncing up and down or simple harmonic motion happening here. Okay, so that's again always very important. We just take it for granted in these questions because we never have extensible strings in pulleys and wedges. We are then told it passes over a smooth, light, fixed pulley at the edge of the table. And again, smooth meaning no friction with the pulley. And we're told then that we have a particle of mass 8 kilograms hanging freely under gravity. And so the coefficient of friction between the 4 kilogram mass and the table is 1/4. So that's our value for mu. So we're told the system starts from rest, so its initial velocity is going to be 0, and the 8 kg is going to move vertically down. So if we were to mark in all of the forces on this overall diagram to give us an overall picture, we would see that we're going to have tension. Tension always acts away from the object. And because it's a common string, we have common tension. We're going to have weight, so the 4 kg acting down, mass times gravity gives us our weight, and same here for our 8 kg, so that's going to be 8g. And then of course we're going to have a normal reaction where the table and the block are in contact with each other. We're going to call that or, and because the table is rough, we're going to have friction. And friction will always act in the opposite direction to motion. So of course, if it's going to accelerate to the right because the block is going to accelerate down, then friction will act to the left. So now we have our overall diagram. What we're going to do is we're going to break that down into the two different particles, the 4 kg and the 8 kg block. And we're going to draw our force diagrams for each of those, even though we're not asked for them. It's always important to do out each individual particle and the force diagram acting on each, because that's going to allow us to set up our equations and then solve our simultaneous equations for, in this case, the tension and the force. Okay, so if we look at the 4 kg first of all, well, what we have is we have the 4 kg on the table, and we saw that we have normal reaction, and we have the weight, and we have tension, and then we have friction. And we know it's going to accelerate to the right, which is going to allow us to see what our leading force is then. So first of all, we have our up forces must equal our down forces, because this block is not lifting up. And therefore that means that or must equal 4g. Now we know that we have friction is equal to, F is equal to mu or, and mu we're told is 1/4. So therefore F must equal 1/4 times 4g, so F must equal g. So now if we're looking at our left equals our right forces, or in other words, F equals ma, and we're looking at our net forces. Well, what we have is the leading force is going to be the tension. The opposing force is the friction. So the net force must equal mass times acceleration. And of course, F we know already is g. M is the mass, is 4, and A is the acceleration. So therefore we can say the tension is equal to 4A plus G. We're going to call that equation 1. Okay, so now we're going to look at the 8 kg block, and we'll do again a nice force diagram for that. So with our 8 kg, we saw that we only had two forces acting on it. So we have the tension acting away, and we have the weight acting down, and it's going to accelerate down, which will tell us our leading force. Now, we only have our net forces in the up-down direction. So again, if F equals ma, because it is accelerating down, we have to look at the net force. So the leading force this time is the weight minus the tension. And the weight in this case is 8g. The mass is 8 and the acceleration is a. So if I rearrange that, I end up with T is equal to 8g minus 8a, sorry. And that's equation 2. So now I have two equations in terms of T. So I'm going to equate 1 and 2. And if I equate 1 and 2, I end up with g plus 4a is equal to 8g minus 8a. So that gives me 12a is equal to 7g, and therefore the acceleration is 7g over 12. And of course then what I'm looking for in the question is the tension. So I only have acceleration here, so I'm going to have to sub a back into either 1 or 2. So I'm going to sub into 1, it doesn't matter which one. And if I sub it back into 1, I have T is equal to G plus 4 times A, which is 7G over 12. And therefore T ends up equal G plus 28G over 12, which is 10G over 3. Okay. So the next part of the question is to find the force exerted by the string on the pulley. Okay, so the string acting on the pulley, well, if I have tension acting away from the block, tension always acts away from the object, but because if we look at that diagram, let me use green here, we're looking at the pulley, well, then the tension is going to act away from the object. So this time, because we're focusing in on the pulley, our diagram will be our pulley, and again our string, so the tension is going to act away and away. So therefore the net force will actually be the resultant of this diagram. So in other words, if I complete my parallelogram there, my resultant is basically going to be a bit of Pythagoras, because again these two sides are opposite and equal in a parallelogram. So what I essentially end up with is Pythagoras. So if I draw that out separately, we have T, T and F, which is our hypotenuse, opposite and our adjacent. And then what we can say is that the hypotenuse is equal to O squared plus A squared. In other words, F is equal to the square root of T squared plus T squared, which is 2T to be squared. But we know that T is 10G over 3. So therefore that gives me 100 G squared over 9. And therefore F, if I simplify that, is going to be 200. Well, if I get the square root of 200, that's basically 10 root 2. And if I get the square root of G squared, that's G. And if I get the square root of 9, that's 3. And of course you could write that in decimal, which would be 46.2 newtons. So if we're looking for the marks overall for the question, we had 5, 10, 15, 20, 25 marks. And we were getting 5 for setting up our first equation, 5 for setting up our second equation, 5 for equating, and 5 for getting our tension out. And then there was only 5 marks going for the last part of the question. So nice little question that.